Okay, graphs are a very important tool that are used in science very often. And in particular, we want to look at position versus time graphs and what information can be determined from them. So moving in 3 dimensions is an unnecessary complication. So let's just look at motion along 1 dimension. And so sort of you can imagine the idea of a cart which is able to move back and forth, and but it's constrained to move only to the left or the right. So maybe it's on a track. And so on this track I have imposed an x, y coordinate system, but the cart can only move on the x values. And so this is an experimental setup. You can see actually there's a sensor here that can tell you where the car is along the cart, and it can send it out to a computer, and we can actually make a plot of what the motion looks like. Now, one of the things that you can see is that if this is where the cart starts to move, the cart is not at the origin. So the position, the initial position is not 0, but some other value. And then the cart might move in the positive direction, it might move in the negative direction, it might go to 0, it might go to negative values from our origin. But whatever way it goes, it's going to be constrained to move in a straight line. That's called one-dimensional motion. And we're going to see that all the things that we learn about one-dimensional motion apply equally in two-dimensional motion and three-dimensional motion. All these concepts work the same way. So it's sometimes easier to just consider the one-dimensional case and then extend it to the other dimensions if you need to. So let's consider a possible graph of the position of a cart versus time. And so we can look at this. We've got x of t, that's position, the x position as a function of time, versus the time. Now normally this is like the y and this is the x, but here we're measuring the x and we're measuring it versus time, not versus another position. And so what that means is I've got my stopwatch running, and when I first start, the cart is over here, so it's away from the 0. It's a positive value to the right of the 0. And then what happens to the cart? It moves in the negative direction, so the cart comes down here. It passes the 0. This would be the x equal to 0 position right here. And so that means the cart's right there. And then it goes into negative values of position, then it turns around. You can see that it's got to turn around right there, and then it reverses direction, and it goes, it's still moving negatively, but then it gets back to the origin, then it has positive values, and then it goes back here where it is at the x equals to 0 position again, so that would be where it would end up on this graph. So if we pick any 2 points, so here are 3 points that we're interested in, point A, point B, and point C, we can talk about the slope of each of those lines, the line from A to B, the line from A to C, and then this green one, the line from B to C. So just as an example, let's consider the green line, the one from B to C. So if we consider this value here and that value there, this would be some delta t, because I've got a starting time here, and if I project it down where my c is, that would be where the ending time is. I'm a little bit off, but you get the idea. This here would be my delta x, and so here, this value here, that would be my starting position, and if I take this c value here and I go directly across, I could mark right there, that would be my final position, more or less. And I could see that there's a delta x from my starting point to my ending point, just as there's a delta t. And if I look at delta x over delta t, that would be the rise over the run of this green segment. And delta x over delta t, that would be the slope of the line. But we know something else that delta x over delta t is. That would also be the average velocity. And so this tells you that if I'm plotting, again, what am I plotting here? I'm plotting position versus time. And so if I want to plot position versus time, the slope of the line is going to represent the average velocity between any 2 points. Now, if we look at the 2 red lines that we have here, the one from A to B and the one from A to C, those have a negative slope. And so that would indicate negative average velocities, but the slope from the B to C is actually a positive slope, and so that would indicate a positive velocity. Now, again, what does a positive or a negative mean when you're talking about a vector quantity? And again, these are vectors. Remember, the positive or negative, it just tells you the direction. It's moving how we've defined the positive direction. And so we had our track that we had our picture of, and we drew our coordinate system, and we defined that direction as the positive x direction. And so all the positive or negative tells you from the slope is whether it's going to the right or to the left on our one-dimensional track. So let's look at an example. We have a plot of position. We can see that's x is position, and it's the position is going to be in meters. And then we have versus time, and the time is going to be given in seconds. And this purple graph here shows the motion, the position as it's changing with time. And so it has a positive value, then it is flat, and then it has a negative value. And so we just simply want to calculate the average velocities over those three segments when the line is straight and has a constant slope. So from t equals 0 to 1, from t equal 1 to 3, and then from t equal 3 to 6, we want to figure out what's the average velocity in each of those times. And of course, that's just going to be the slope of the line, the rise over the run, or the change in position divided by the change in time. So for the first segment, from 0 to 1, we can see directly from the graph, from here to here is 1 second, 1 tick of the clock, and from there to there is 2 meters, because this is in meters, each tick is a meter. So that means that we've got our final position is 2 meters, our initial position was at the origin, 0. It's from 1 second to 0 seconds, that gives us 2 meters per second. It's just the slope, 2 to 1. The slope tells us the average velocity. And we can see that the slope is positive here, so that would tell us that it's a positive slope, or a slope in the positive direction. Or, sorry, a velocity in the positive direction. Here we can look at the other two segments, the flat segments. And so what's the initial position? If we go over here, we can see it's 1, 2, so that's 2 meters. And it's 2 meters the whole time, and it's certainly 2 meters at the final position. So to get the average velocity, we do the final position, 2 meters, minus the initial position, 2 meters, divided by the change in time. So here we start at 1 second, and here we end up at, that's 1, that's 2, that's 3, so that ends up at 3 seconds. So the delta t is the final time minus the initial time, 3 minus 1. That gives us 0 meters divided by 2 seconds, but of course if 0 is in the numerator, that makes the whole thing 0 meters per second. Now, you could have figured that out without doing any of this calculation, because what's the slope here? The slope of a horizontal line is by definition 0. And so you could just look at that graph and say, by inspection, those are fancy physics words for, I just looked at it and saw it. By inspection, the average velocity is 0, because the slope is flat. And then the last portion of the graph, we can see that it is got a negative slope. So let's see what if that shows up in the math. We can again plug in x final minus x initial. The final position is 1, 2, 3 down, so that's negative 3. And the initial position was 1, 2 up, so that's going to be minus 3 is the final position minus the initial position, which is 2, divided by the time, 6 seconds. That's 1, 2, 3, 4, 5, 6. So this is at 6 seconds minus 3 seconds. And we end up with 1.7 meters per second in the negative direction. Again, that negative always tells us the direction. And we see the slope is negative, so that makes sense.